Okay, hello everyone. So we are from group number 26. So my name is Hassan and I'm here also with Nordin. And today in this change we would like to present about our data mining paper presentation. So basically we have chosen like 3 papers in here, and this is the first paper, and the first paper title is LEX-GNN, which is Label Exploring Graph Neural Network for Accurate Fraud Detection. And this paper was written by a researcher from Seoul National University in Korea, and it talks about a smart way to detect fraud using GNN. And this is the outline for presentation. We have motivation, contribution, method, result, conclusion, strength and weakness, and also the future work. And let's start with why this paper matter. And the detection fraud is basically hard because there are very few fraudsters, and they try to hide by connecting with normal users, and this make it's difficult for traditional model like regular GNN, which assume the connected nodes are similar. And also some past method try to fix this by removing suspicious link or only using similar neighbors, but they don't use most of the data, especially the unlabeled nodes, which are actually the majority. And so this paper asks basically like, what if we could guess which nodes are likely fraudsters and use that to guide the learning process. And for the contribution, this paper introduced like a new model called LEX-GNN. It basically does three key things. First is it predict whether each node is likely to be a fraudster. Like this is called a soft label in this paper, and it changes how information is passed between nodes depending on this prediction, and also it works really well even when only 1% of nodes are labeled, which is really great for real life situation where we don't have much label data. And here's how LEX-GNN works basically in simple terms. In a normal GNN, every node sends to same kind of message to its neighbor, but LEX-GNN is smarter. It first estimates the change each node is fraudster, and then it customize how that node sends and receive information based on the prediction. And this basically makes the model more accurate, especially when fraudsters are trying to hide. And the first step is basically to predict how likely each node is a fraudster. The model uses a simple neural network to give each node a score between 0 and 1. And then it uses real label data to help this prediction to get better comparing the score with the known label. And basically this prediction is important. It tells us that the model how to treat each node in the next step. And next, LEX-GNN also use those fraud scores to change how information is shared. First, if a node looks suspicious, its message gets adjusted differently than a normal one, and then the message it sends is also modified using fraud specific weight. And also finally, an attention mechanism help the model focus on the most important neighbors, based on how trustworthy they look. And this makes the message passing much more flexible and fraud aware. And after all layers are processed, the model makes the final fraud prediction, and it used two loss function in here. First one check if the final prediction is correct, and then another one is the other check if the fraud score prediction is close to reliable. And the total loss is the combination of these two. This lets the model learn from both the label nodes and the soft label cases. And to test the model, the author basically used two datasets, like Yelp dataset with online reviews, some of which are fake, and another dataset is Amazon with user data, where some users also are fraudsters. And they also tried on two situations. One where 40% of the nodes are labeled, and another one more realistic one with only 1% labels. They also use like a standard training settings and build the model using PyTorch and DGL. And this is the result. This table basically shows us how LEX-GNN compares with 6 other fraud detection model like this. And in every case, LEX-GNN basically got the best result with higher AOC and also F1 macro scores. And even with a 1% levels, it still outperformed with compared with others models. That means that it's very strong, and even when we don't have much data to train on. And this graph shows how important the fraud score prediction are when the model doesn't use them at all. Like it means that the beta equals to 1, so the performance is worse, but as soon as it starts learning the scores, the result will be improved. And even if the guesses are not perfect, they still help guide the model better, especially when the label data is limited. And to wrap up, LEX-GNN basically is a new way to detect fraud on graph. It doesn't just look at who connect to whom. It also gets like how suspicious each node is, and it also used that to change how information flows. And this approach works great even when there are very little label data. And it also handles cases like where fraudsters are trying to hide among normal users. And talking about strength and weakness, for the strength, it's a new idea like that mixes label prediction with message passing, and it's based on solid design and experiment, and also it worked really well even with very few label. Like previously it's like only 1% label. And for the weakness, the model is more complex than basic GNN, of course, and it hasn't been tested on the really large graphs, and it only has 2 datasets were used, which is like more testing will help prove it works in general. And so that's why for the future work, maybe we can test like on the larger graphs to see how it scales. And also maybe we can try like to make the fraud prediction more reliable, like maybe by adding confidence level. And then also it can be try it on like other types of graph like social media, which are often very messy and sparse. And to wrap up our my presentation, we have some question about this paper. Like first, how well would LEX-GNN perform on much larger graph, like those with millions of nodes and edges? The paper didn't mention any larger scale benchmark, so I am curious if the dual transformation and intention mechanism will still be efficient. And the second, can LEX-GNN adapt over time if fraud pattern change? In real life system, fraud behavior evolve, and it will be interesting to know how this model could handle that. And lastly, since the model depends on soft level prediction, what happens if those predictions are wrong, and how sensitive is the overall performance to this error? And for the second paper, I will talk about the paper called ADOD, which is Adaptive Density Outlier Detection. It's a method designed to find strange or rare data points, which is commonly called outliers, in a smart way and flexible way. And let's start with the motivation, which is like basically commonly outliers can mean something important like fraud in banking or error in medical data, but many existing methods like KNN and LOF don't work well when the data is spread out unevenly. Like some areas are dense and others are not. So this kind of thing, this older method use fixed settings that don't adjust to the shape of the data. So the author of this paper asked like, what if we could automatically adapt to different data shapes and still find the outliers accurately? And here's what this paper contributes. First, it figured out how dense area is for each point using something called perplexity, which is they inspired by TSNE method. And the second, it scored how unusual a point in by comparing it to its neighbor. And the third, it builds a special graph to link points that are truly close to each other. And next one, it used a faster research method to handle large dataset. And also the last one, for overall, it outperformed other popular outlier detection method on 32 real-world datasets. And for the proposed method, the first section is adaptive density estimation. And ADOD basically looks at each data point and decide how wide its neighborhood should be, like drawing a circle around it. And it doesn't use a fixed size for everyone. And instead, it used perplexity to estimate how many nearby points should matter. Then it calculates a radius that adjusts based on local density. This means that it can handle both dense and sparse area properly. And next, ADOD connect like each point with its mutual neighbors, those that are close to each other, and it then calculates how dense each point area is, and finally it gives each point an outlier score. If it's much less than its neighbor, it gets higher score, meaning it's likely an outlier for that case. And to sum it up, ADOD basically has three smart things. First, it adjusts how many neighbors each point should consider. Second, it builds a graph of strong mutual connection, and it scores each point based on how different it is from its neighborhood. And the author tested ADOD on 32 different datasets from fields like health, finance, and web. They compared it with 14 other methods, including well-known like LOF and KNN, and they used performance measures like ROC and P at N to check how well each method did. And this is the result of their purpose method. It did like really well in the test. It was best method in more than half of dataset for both ROC and P at N scores. Even better, it didn't need much fine tuning, like so the as we can see in the visual chart also showed that ADOD could clearly separate outlier from normal data. That means it's accurate and stable. And to wrap up the presentation, this is the conclusion. First, ADOD is a unsupervised method, which means that it doesn't need label data to find outlier. That's really useful in real-world situations where labels are hard to get. And instead of using fixed neighbor in the traditional method, it uses perplexity to adjust how many neighbor each data point should consider. And then it calculates how unusual a point is by looking at local density and comparing it with its neighbor using what they call like density consistency scoring. And also the results show that ADOD works really well. And one of the best part is that it works without needing a lot of parameters. So overall, like ADOD is accurate, robust, and ready to be used in practical outlier detection task. And what's great about ADOD, it brings a new idea using perplexity from TSNE for outlier detection. It's carefully designed and work well in practice. It performs the best on many real-world datasets. And what could be better? Without optimizing, it can be slow for very big dataset, and it still depends on some default setting like perplexity, and it may not work well on really high dimensional or messy data. Like maybe if we try on like 3D data, it could be we could get a different result. And for the possible future work, maybe we can try and make it even faster by improving the algorithm. And the second, maybe we can try like automatically choose the best perplexity setting, because for right now we need to like fine tune it. And to maybe we can make it work for real time or streaming data. And also maybe we can apply it to other kinds of data like time series or graphs. And if I could ask the author, I would like to ask like, can ADOD work well on live data stream where the data keeps changing, and will it still be reliable on really large or sparse data with a lot of missing info? And if the neighbor search is a bit off, will the data affect the result a lot? Yeah, for the last paper, the title is Rank Supervised Contrastive Learning for Time Series Classification. It basically introduced a new way to improve constructive learning by using ranking information to make time series classification more accurate and effective. And let's start with the motivation again. Time series data is everywhere, like from health and sensor to finance, so it's everywhere. Constructive learning has been helpful when we don't have many labels, but existing method treat all positive pairs the same, which is not ideal. Some are more helpful than others. This paper wants to fix this kind of thing by ranking positive pairs based on how useful they are and giving more weight to the better one. And the goal is to learn clearer and more accurate features for classification. And this paper brings some contribution, a new method called rank SCL that use ranking in constructive learning, and is also a rank based loss to weight positive sample differently, and a new data augmentation method in the embedding space. And they also contribute on a smart way to pick good triplets for training. And finally, it beats other top method on 128 unvariate and 30 multivariate datasets. And for the proposed method, the rank SCL model works in several steps. Basically, first, a three-layer convolutional network turns the time series into features. Then a projection head maps those features into an embedding space based on labels. It picks positive and negative pairs. It also supplies data augmentation to the embeddings. Then a new ranking loss is used to learn which pairs are most useful for training. Instead of changing the raw time series, this method adds small noise to the embedding directly. And basically, like for instance, like each embedding zi gets jitter with to alpha value, it will create new view for per sample. So it will help the model learn stronger and more general features. And in constructive learning, we usually compare an anchor with one positive and one negative. So in here, they only choose valid hard negative, meaning that the negative is closer to the anchor than the positive. This basically helps the model focus on tougher examples, like those where the difference between classes is less obvious. And now the core idea, basically ranking the positive sample. Same positive sample are more useful, especially the one with fewer close negative samples. And they test their proposed method on two big benchmark, 128 UCR dataset and also 330 UAA datasets. And they compare with popular method like InfoTS, TS2FAC, and DTW. And they also use like some metrics in here. And yeah, this is the implementation hardware they use and some parameters here. And on on UCR dataset, basically rank SCL slightly improve over TS2 FAC in F1 precision and recall, but on UAA it shows even bigger gains, up to like 3.5% improvement in recall. And this shows that the method works really well, especially with more complex data. And for the conclusion, this proposed method is a constructive learning method for time series classification. It adds smart data augmentation, ranks how useful each training pairs is, and focus on learning from the best one. And for the strength, it's new, and also it's technically sound with strong design and testing. It's also effective, beating top methods across many datasets. And for the weakness, it uses fixed setting for augmentation, which might not be optimal, and computing ranks can be slow for large batches, and it hasn't been tested on real-time or streaming data yet. And yeah, this is some possible ways to improve this work in future. Maybe for automatically choose the best augmentation setting, make it work for unsupervised or semi-supervised learning, and maybe we can try it on like other data type like sensor fusion or multimodal inputs, and maybe we can speed up training when using a larger data set. If I could ask the author a few questions, maybe first, how sensitive is the model to how many augmentation we add, or how strong they are? And could the method work well without any labels at all, like in an unsupervised setup? And how does it handle noisy or wrong labels, and also can we adapt this model for real-time application where data arrive continuously. Yeah, and that's all for the paper's presentation. Yeah, thank you.